not be enough to make such a lime ball as big as the sun is. No, you must make it as big as 146 suns, or more than 146,000,000 times as big as our earth, in order to get the right amount of light. Then you would have a tolerably good artificial sun, for we know that the body of the sun gives out an intense white light, just as the lime ball does, and that, like it has an atmosphere of glowing gases around it. But perhaps we get the best idea of the mighty heat and light of the sun by remembering how few of the rays which dart out on all sides of this fiery ball can reach our tiny globe, and yet how powerful they are. Look at the globe of a lamp in the middle of a room, and see how its light pours out on all sides and into every corner. Then take a grain of mustard seed, which will very well represent the comparative size of our earth, and hold it up at a distance from the lamp. How very few of all those rays which are filling the room fall on the little mustard seed, and just so few does our earth catch of the rays which dart out from the sun. And yet this small quantity, 1/2000,000,000th part of the whole, does nearly all the work of our world. In order to see how powerful the sun rays are, you have only to take a magnifying glass and gather them to a point on a piece of brown paper, for they will set the paper alight. Sir John Herschel tells us that at the Cape of Good Hope the heat was even so great that he cooked a beefsteak and roasted some eggs by merely putting them in the sun, in a box with a glass lid. Indeed, just as we should all be frozen to death if the sun were cold, so we should all be burnt up with intolerable heat if his fierce rays fell with all their might upon us. But we have an invisible veil protecting us, made of what do you think? Of those tiny particles of water which the sunbeams draw up and scatter in the air, and which, as we shall see in Lecture 4, cut off part of the intense heat and make the air cool and pleasant for us. We have now learned something of the distance, the size, the light, and the heat of the sun, the great source of the sunbeams. But we are yet no nearer the answer to the question, what is a sunbeam? How does the sun touch our earth? Now, suppose I wish to touch you from this platform where I stand. I can do it in two ways. Firstly, I can throw something at you and hit you. In this case, a thing will have passed across the space from me to you. Or secondly, if I could make a violent movement so as to shake the floor of the room, you would feel a quivering motion, and so I should touch you across the whole distance of the room. But in this case no thing would have passed from me to you, but a movement or wave which passed along the boards of the floor. Again, if I speak to you, how does the sound reach your ear? Not by anything being thrown from my mouth to your ear, but by the motion of the air. When I speak, I agitate the air near my mouth, and that makes a wave in the air beyond, and that one, another, and another, as we shall see more fully in Lecture 6, till the last wave hits the drum of your ear. Thus we see there are two ways of touching anything at a distance. First, by throwing something at it and hitting it. Second, by sending a movement or wave across to it, as in the case of the quivering boards and the air. Now the great natural philosopher Newton thought that the sun touched us in the first of these waves, and that sunbeams were made of very minute atoms of matter thrown out by the sun, and making a perpetual cannonade on our eyes. It is easy to understand that this would make us see light and feel heat, just as a blow in the eye makes us see stars, or on the body makes it feel hot, and for a long time This explanation was supposed to be the true one. But we know now that there are many facts which cannot be explained on this theory, though we cannot go into them here. What we will do is to try and understand what now seems to be the true explanation of the sunbeam. About the same time that Newton wrote, a Dutchman named Huygens suggested that light comes from the sun in tiny waves, traveling across space much in the same way as ripples travel across a pond. The only difficulty was to explain in what substance these waves could be traveling, not through water, for we know that there is no water in space, nor through air, for the air stops at a comparatively short distance from our earth. There must be something filling all space between us and the sun, finer than either water or air. And now I must ask you to use all your imagination, for I want you to picture to yourselves something quite as invisible as the Emperor's new clothes in Andersen's fairy tale, only with this difference, that our invisible something is very active, and though we can neither see it nor touch it, we know it by its effects. You must imagine a fine substance filling all space between us and the sun and the stars, a substance so very delicate and subtle that not only is it invisible, but it can pass through solid bodies such as glass, ice, or even wood or brick walls. This substance we call ether. I cannot give you here the reasons why we must assume that it is throughout all space. You must take this on the word of such men as Sir John Herschel or Professor Clerk Maxwell, until you can study the question for yourselves. Now, if you can imagine this ether filling every corner of space, so that it is everywhere and passes through everything, ask yourselves what must happen when a great commotion is going on in one of the large bodies which float in it. When the atoms of the gases round the sun are clashing violently together to make all its light and heat, do you not think they must shake this ether all around them? And then, since the ether stretches on all sides of the sun to our earth and all other planets, must not this quivering travel to us, just as the quivering of the boards would from me to you? Take a basin of water to represent the ether, and take a piece of potassium, like that which we used in our last lecture, and hold it with a pair of nippers in the middle of the water. You will see that as the potassium hisses and the flame burns round it, they will make waves which will travel all over the water to the edge of the basin, and you can imagine how in the same way waves travel over the ether from the sun to us. Straight away from the sun on all sides, never stopping, never resting, but chasing after each other with marvelous quickness, these tiny waves travel out into space by night and by day. When our spot of the earth, where England lies, is turned away from them, and they cannot touch us, then it is night for us. But directly England is turned so as to face the sun, then they strike on the land and the water, and warm it, or upon our eyes, making the nerves quiver so that we see light. Look up at the sun and picture to yourself that instead of one great blow from a fist causing you to see stars for a moment, millions of tiny blows from these sun waves are striking every instant on your eye. Then you will easily understand that this would cause you to see a constant blaze of light. But when the sun is away, if the night is clear, we have light from the stars. Do these then too make waves all across the enormous distance between them and us? Certainly they do, for they too are suns like our own, only they are so far off that the waves they send are more feeble. and so we only notice them when the